Hi friends, welcome back. Now onwards we will also work on featureization and model tuning and selection. So basically we will see now region lasso regression. The sample code is for region lasso regression. So basically what the region lasso regression is, these are nothing but the regularization technique used to prevent overfitting in linear regression model. So here we add a penalty term to the loss function. Yes, we will of course see it later on this video, right? So before wasting time, let's start one by one how the practically we can apply region lasso regression. And here we will have problem statement and we will be solving those statement based on region lasso. So here we are importing the matplotlib numerical libraries, right? And that is numpy. Then importing linear regression machine learning library like linear regression, reach, lasso. Then we are importing r2 score, right? Then to handle data in form of rows and column, we are importing pandas as pd, importing plotting libraries matplotlib.pyplot as plt, and importing seaborn for statistical plots. So we normally import seaborn as sns. Now let's do what. So mpg.df equals to pd.read csv. So this is the csv that will be provided in the link that will be provided in the description also. Now mpg.df equals to mpg.df.drop. So here we are dropping car name, access equals to 1, that means will drop permanently. Now mpg.df origin equals to mpg.df origin dot replace. 1 is for America, 2 is for Europe, 3 is for Asia. Now mpg.df equals to pd.get dummies, right? mpg.df columns equals to origin. mpg.df equals to mpg.df.replace function we are calling, right? With the semicolon and where np.none. Now mpg.df equals to mpg.df.apply lambda x x.fill na x.median and x is equals to 0. Now separate independent and dependent variables. So copy all the predictor variables into x data frame. Since mpg is dependent variable, drop it. Now x equals to mpg.df.drop mpg.access equals to 1. Now copy the mpg columns alone into the y data frame. This is the dependent variable, y equals to mpg.df mpg, right? Now from sklearn import preprocessing. So scale all the columns of the mpg.df. This will produce a numpy array. So x scaled equals to preprocessing dot scale x scaled equals to pd dot data frame x scaled columns equals to x dot columns. Now ideally the training and test should be right with the x scale. Now the y scale will be preprocessing dot scale y obviously, and y scale equals to now pd dot data frame for y scale this one, and column equals to y dot column. So this is basically for our training set. Now let's do a train test split by importing the model selection, right? By importing the train test split from model selection. X train x test y train y test equals to train test split. X scaled y scaled test size equals to 30%. That means training size will be our 70%. Random state equals to 1, that is an integer, so which will hold the state of our train test split. Now fit a simple linear model. So again calling linear regression, storing it into the regression model, right? And fitting the x train y train in the linear regression. Now iterating a for loop idx column name in enumerate x train dot columns. So print the coefficient for this column name and regression model dot column of 0 and index, right? So this will be the coefficient for cyl is this one, this for this one. So these are nothing but the attribute in our data set for our x-train column, and this is how the coefficient looks like for them. Now we are importing our interception. So intercept equals to regression model dot intercept for 0. Now printing the intercept for our column is for format in this intercept. So this you can see the intercept for our model is we are getting 0.019 approx. Now creating a regularized ridge model and note the coefficient. So let's start by creating a ridge model, again defining the variable ridge, right, calling the ridge function and passing the alpha value as zero point 0.3. Now ridge dot fit x train y train, okay, printing ridge model, that is ridge dot coefficient. Now ridge model equals to, so here you can see that all these value we are getting for our ridge model. Now create a regularized lasso model and note the coefficient. So lasso equals to lasso, right? Similarly doing for alpha as 0 0.1. Here we have passed 0.3, but for lasso we are passing the less value of alpha. Now lasso dot fit x train y train, printing lasso model, so lasso dot coefficient. So observe many of the coefficient have become 0, indicating drop of those dimension from the model. So lasso model, if we talk about, so here you can see that we get all the values. Now let us compare their score. So if we talk about our regression model, right, and here this is the mean regression model that we are getting for train, we are getting 83%, for test we are getting 85% nearly, for reach we are getting 83% again, for and test again we are getting 85%. But you can see there is a slight difference between both the train and test values, right? If we also talk about lasso, so the difference can also be seen. So 82,114 here, 83,43, 83,4377, right? So this way the difference and the reason lasso difference you can compare from this score. Now more or less similar result, but with less complex model, of course. So complexity is function of variables and coefficient. So with lasso we get equally results in test throw, not so in training. Yes, of course, we can see here. So the number of dimension is much less in lasso model and then ridge or unregularized model. So let us now generate polynomial model reflecting the non-linear interaction between some dimensions. So from sklearn dot pre-processing, again importing polynomial features. So poly equals to polynomial features, degree equals to 2, interaction only equals to true. So here you can see x poly, poly dot fit transform, x scaled, x train, x test, y train, y test. So train test split, x poly, y test size equals to 30% and random state equals to 1. Now x train dot shape, so this is the shape 278 by 56, okay. Now fit a simple non-regularized linear model on poly feature. So regression model dot fit x train y train, so print regression model dot coefficient 0. So here you can see that all the value we get from here for our regression model coefficient. Now ridge equals to, again ridge alpha equals to 0.3, ridge dot fit x train y train, printing a ridge model, that is ridge dot coefficient. So here again you can see all these value for ridge model as well. Now ridge dot score x train y train, ridge dot score x test y test. So 0.91% and 0. That means 91% for ridge score and ridge score for x train y train, and 86% for ridge score x test y test. Now similarly lasso equals to lasso alpha equals to 0.01, lasso dot fit x train y train, print lasso model, lasso of coefficient. So lasso model you can see from here, right? Now print lasso dot score x train y train and print lasso dot score x test y test. So the lasso score for x train y train we got 90%, and the lasso score for x test y test we got 86%. So hope you could get the idea how can we apply ridge and lasso regression for any particular problems statement, and we'll come up with more example regarding to FMT or featureization and model tuning. So let's continue the series. Stay tuned. All the best. Thanks.